So let us start discussing about this additive manufacturing, about the present and future. We learn everything about what we're going to see about this wonderful topic, additive manufacturing. We call this one also as ADAM, additive manufacturing. Okay, so let us see. So there are a few things that we'll learn about the contents. So let us see the content part. So the first thing is about the introduction. We'll see everything about that, and few things about what additive manufacturing is all about the functional principle, about the advantages and disadvantages, about the applications, and thirdly we'll learn about the process. What are the major process that is in additive manufacturing is, and what are the present conditions that's been happening, the present scenario, and what are the future aspects are all about, and what are the gaps that need to be filled, and finally recommendations and conclusions. So let us, without much delay, let us move forward. So manufacturing of this goods was mainly done with either two processes, either addition or subtraction. In ancient days we used to subtract either by lathe and all that. Even if we do metal casting, even then we need to subtract by removing the unnecessary parts. But after this comes additive manufacturing, we create something from scrap. How does it work? Let us see one by one. So the first thing here is technology. So by using the technology, either CAD or else many other softwares, we can use additive manufacturing as a major tool. Also, secondly, it eliminates many constraints imposed by conventional manufacturing. So conventional manufacturing, there is so much of delay in time, and also there is so much of need of labor, and it's a tedious process which is very timely process, and we need also strict visualization. But here the additive manufacturing just remove it all of a sudden. And comes third thing, it leads to more market opportunities. So we can do at anywhere in your homes, we can do this. So there is so much of market that is available for this. And finally, it increases the applications such as 3D facing center scans, also different sort of digital images in layers also. So we'll be seeing one by one about how this works and how this layer by layer image just works. Okay, let us go ahead and go forward. So here, as you're gonna see something that what exactly is additive manufacturing is all about. So the main definition that we can see here is the process of joining materials to make objects from 3D model data. So basically it's a joining process such as a welding process kind of thing, but it's joining materials to make objects from 3D model. It is also by layer by layer. That is main thing in additive manufacturing. Layer by layer joining materials 3D. It is also called as 3D printing, and no geometric limitations or tools are used here. So additive manufacturing used as an additive process, as the name indicates itself. We use it as a additive process. So we'll be seeing one by one about what are the manufacturing process or designs are, how it is distinguished from the traditional subtractive machining techniques, as I told you before, how we subtract in the earlier tradition process. But here there is no such sort of machining, there's not such sort of any finishing. Okay, directly we get the desired shape, and actual shape from additive manufacturing is this thing. Okay, so this is the major thing we can get in here. So let's see what are the major things. So the first thing here we can see is it is a materials development. So how the materials develop is the 3D AutoCAD model. So we can see it here, and we design and modulate and stimulate it. So it is called .stl file. Okay, just remember it, .stl file. Maybe if you are doing CAD or anything else, you might know this. So second thing is about designing, modeling and stimulating. We call this one as DMS. design, modulate, and stimulate. And thirdly, what we can do is in the same thing we slice it. There is also something called slice formula. So we just design .stl file and put this in the software of sliced so that we can slice it so one by one, and there's a tool path, so we'll do it. And thirdly, what we do is it is a material processing and layering, so that is called 3D printer. Okay, here it takes processing and layering. Okay, two things happens here. This one thing is processing, the second thing is layering. So first thing, materials development, how we develop in the CAD model. Second thing, .stl file and slicing layer. And third thing is about material processing and layering. Finally we get the final product. Okay, so that is a 3D object, so you can see it in 3D CAD model and 3D object. So what are the functions that we're going to use here? So the first thing that we can see here is it's all about how the system starts by applying a thin layer of the powder material to the building platform. So there is so much of discussion being taken to the about how a thin layer of powder material is being built across a platform. And second thing, it's all about how a powerful laser beam fuses powder to exactly the points defined by the computer generated component designs data. So first thing is the thin layer of the metal powder is being building a platform, and second thing is the laser beam is fusing to the exact points. Okay, so exact points. And third thing is the platform is lowered and then another layer of powder is applied. It is lowered and another layer of powder is applied. Finally, once again the material is fused so as to bond with the layer below the predefined points. So we'll see one by one about this, but the four things is common: material development, design and modeling and stimulating, DMS, and metal processing and layering, and final product. So let us see what the advantages and disadvantages are. See, in every process there is some sort of advantages, some sort of disadvantages. It's the same thing in additive manufacturing also. There are few advantages and disadvantages. So what are these? So first thing is freedom of design. So we can just design whatever we like. Okay, any design, freedom of design. And complexity, any complex material can be done. And elimination of tooling, so no need of tooling, so it can be done without any tooling. And lightweight design, so we can get it very lightweight. Mainly it is used in army, navy, air force, defense, and also aerospace industries. Elimination of production steps, so we need not again we need not put everything, like no need of finishing, no need of machining, no need of assembling. Okay, so the production steps gets decreases. So but what are the disadvantages? So the first and foremost disadvantage here is slow build rates. So it takes me much time because of the advancements we need but we couldn't have. So second thing is high production rates costs. If we take a small product, see, even to design we need someone, even we just said right DMS. Okay, so even for DMS we need someone, and even for the processing at 3D printing we need someone, and for the final product we need someone. So for small products it's not much useful, so if you use for big products it'll be useful. And third thing, considerable effort required for application design, so it's need of that. And discontinuous production process, so it's not a continuous one, it's discontinuous, so it's also a limitation here for us. And the component size also is a limited barrier for us. So what exactly we can get from these applications? So the applications are very important here. As you can see here, the first application, the additive manufacturing has been across wide varieties of industries. So what are the major applications that we can see here is all about how does it works. Okay, in automobile, so even in mainly in Tesla they're using for this, except for the engines, like even for everything else they're using for the automobiles and also cars, bikes. Okay, even cycles. And aerospace mostly is used in aerospace. See, for because of the reduction of the weight ratio and density ratio, we're using mostly in aerospace. And biomedical, so in biomedical also it's been used even in heart, lungs, and few other prosthetics. There are many things that have been used artificially, they are made. Okay, so finally consumer goods, so it can be basically it is custom made, right? So we can just use to buy it, so it is really helpful for us. So let's go to the next. So additive manufacturing processes are classified into 7 categories. So basically these 7 categories are more important because mostly we see these 7 categories. So what are 7 categories? So the first thing we call it as, yeah, let me write it down here, yeah, VPP. Okay, or else we also call it as SL. So stereolithography or VAT photo polymerization. So what is this? We will see in detail. So second thing is material jetting, and third thing is binder jetting, and fourth thing is material extrusion, and powder bed fusion, sheet lamination, directed energy deposition. Okay, these are 7 things. So first thing that the name indicates, stereolithography. We know that lithography is something which denotes how the light rays falls and comes, and it's layer by layer process. And metal jetting also is something which is layer by layer process. Binder jetting, just its the name indicates. So metal extrusion. So we'll see one by one how it works. So first thing here is, as I told you, VPP. Okay, VAT photopolymerization, and also called as stereolithography. Okay, SL. So what is it? So basically what happens here is, you can see in the picture here, so there is something called V platform that we had used here, and this is photoresin, and this is called VAT, the one which is it is holding on. So that's the reason we call VAT photopolymerization. So it is a photoresin, so that's the reason we use the laser, and the object is covered over here by using the same photoresin. Okay, let us see how it works. So laser beam traces a cross section of the part pattern on the surface of the liquid resin. So you can see it, right? So the laser ray, it makes the traces. Basically the first thing that you need to remember is here, the laser beam traces the cross section. And second thing, SLS elevator platform descents. Okay, so as the stereolithography elevates, the platform descends. And the second thing, see, basically it goes down like this. So it takes here and goes down, so it all completed, it's coming down into the resin. So a resin filled blade sweeps across the cross section of the part, recollect coating it with fresh material. And also we use the fresh material, so it goes immersed inside, so it is immersed in a chemical path. So it requires supporting structures like this, like Y platform here. So that's a major thing here. So this is how it works, VAT photopolymerization. And second thing is material jetting. So what is material jetting? So the basic thing here in material jetting is, it's all about drop on demand method. So what is this drop on demand method? So basically the name here indicates so how the drop and demand method works. We'll be seeing it, and also how the print head is positioned above build platform. See, the one thing that you can understand here is, it's all about this thing. Okay, see, it's a leveling blade here, and it's a UV covering lamp here. So basically the leveling blade, just put it aside, and UV curving lamp is here, and what it does is, it basically gives a path. Okay, and there is something called build material or support material, which is used in red color and blue color over here. It is basically dipped into these things. Okay, that is called jetting. Basically, if you know the concept of how the printer works, jet printer works, it will be easy for you. It basically, the jet printer works like this. There will be something like jet like kind of thing. It gives a drop. Okay. Because it's a colorful, so there will be a little bit like colors kind of thing. Okay, anything. So it works like this. So there is something called part support that we'll be using on the bottom region to make it support. So it's called elevator here. So how it elevates, and basically it does work like this. So the UV curving lamp shows a path, and there will be build material. That's it. It's a simple process, same as a printer. Okay, so there we go. So how does it works? So the basic principle here is the material is deposited from a nozzle kind of thing that I told you before, which moves horizontally across the build platform. So what happens here is the material layers are then cured or hardened using ultraviolet light. So that's the reason we use ultraviolet curing lamp here. It helps in hardening. Okay, and then the droplets of material solidify and make up the first layer. So because of this solidification, we just complete the first layer like this, and then second layer, third layer, like this it goes. Okay, so finally the platform descends by using the elevator, and good accuracy and surface finish will be obtained from the material jetting. And then let's go to the third thing. It is binder jetting. So what exactly is the binder jetting? So we know binder, something which binds material, right? So in the same way, how does it works will be, it's a really simple thing. So you can see here, right? So there is something called liquid adhesive supply here. So from here we'll be supplying liquid adhesion material, and then here there's something called inkjet print head. So it goes into it, and then from here it diffuses. How does it goes is that there will be a leveling roller, you can see it over here, and then here there is also a power supply kind of thing. Okay, so when it does, there will be leveling lower. But how does it works? See, it is same as printer kind of thing, inkjet printer, but the one thing that matches here is it builds the parts. Okay, it builds the parts as it goes down, and there will be, like, it rolls and gives. So wherever there is some there is the droplets of this, it builds the parts, and there is the powder bed here and build from here. But basically how does it works? So a glue or binder is jetted from the inkjet style print head. So from here, either a glue or, okay, and then what happens is next is a roller spreads a new layer of powder on top of the previous layer. See, so this roller, what it does is it goes here and it spreads the powder on the top of the layer, and there will be subsequent layer is then printed and is switched to the previous layer by jetted binder. Okay, so the remaining lost powder in the bed supports overhanging the structures, so it will be helpful for the support to be withstanding. And the fourth thing we can see here is it's all about the wonderful thing called material extrusion. So this is the main process that we're using nowadays. It's called FDM. We also call it as FDM as fuse deposition modeling. Okay, we can see it over here, the FDM, fuse deposition modeling. Okay, so what is it? So fuse deposition modeling is all about. So basically you can see it here, right? There will be material spool which will be like this curvy kind of thing, and then it goes down, and there is a heat element. Okay, so it heats it. So, and there is a nozzle over there, and then because it's heating, it just goes down, and whatever it does is it just it just moves wherever it needs, like it. Okay, let me show you. So if you need a phone, like kind of thing, so I'm just putting a phone here, and I need a phone. So what this does it just moves like this. Okay, but I don't need a phone, I need something else, maybe, yeah, a sanitizer. Okay, so what it does is it just goes round 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 round, and here it just goes come narrow because it's a narrow thing, like kind of thing. Okay, it does how it works. So it's a really simple thing, and it's the most prominent thing that we can use nowadays. So okay, so this is how it works. It's a really simple thing. So second thing is the material is run through the nozzles where it is heated and is then deposited layer by layer, as I told you before. So first layer is then built as nozzle deposits material when required cross section. The following layers are then, okay, it's the same thing that I told you. So the fifth thing we're going to see is very important. So because it is a powder bed fusion. Okay, powder bed fusion is the most important thing that we're using these days. Before thing and this one. Okay, powder bed fusion, the name itself says there is a powder that we're going to use here. So there are three important things that we use here. The most tradition for this is we no need of any substructures. Okay, no need of any supporting structures here. That is the main advantage. Okay, so what exactly we're going to see here? SLC. Okay, let us remember like this: SSE. Okay, you know it, right? Staff selection. Okay, so we can remember it as SSE. SS means selective laser sintering, selective laser melting, electron beam melting. Okay, so just remember these three things. First thing is selective laser sintering, selective laser melting, electron beam melting. Okay, no worries, let us see the process. The process is really simple. So there is a powder roller here. And what does it do is there's a new powder stock over here. It just goes up above, and wherever we need, so it's a build platform, so it is basically over here, and it just gives a laser. Wherever the laser is, the powder just be imparting over there because of the laser gives something heat. So there is sintering. As you know, sintering is agglomeration. We will have heat and we will build the material. So this is the powder bed, the actual powder will be there, and it's really simple process. Okay, so typically 0.1 mm thick of material is spread over the build platform. Okay, how much? 0.1 mm. See, it's really small, right? So selective laser sintering machine preheats the bulk powder material in the powder head, so it helps in no other issues. Okay, so a laser fuses the first time in the first layer, and then a new layer of powder is spread, you know it, right, by the powder roller. A new layer of powder is spread, and further layers of cross sections are fused and added. So basically the process repeats until the entire model is then created. Okay, so the sixth thing is sheet lamination. So we are nowadays using sintering. Okay, selective laser sintering, and also this thing called sheet lamination. So the metal sheets are used, and laser beam cuts the contour of each layer. Okay, so it cuts the contour of each of the layer. So glue activated by hot rollers. So let us see how exactly this works. So the process is really simple. The material is positioned in space of the cutting bed. So you can see it, right here. There is a material spool which will be like this and goes above, and it goes above, and this goes above. There's a laser thing. It's a monitorized mirror, so it just gives and it heats up here, and the restore comes over here. This is called the used materials pool. Okay, the restore, and we can use it again here. So how does it works? So it's going to be really simple. So it's positioned in a cutting bed, so the material is bonded in place over the previous layer using the addition. Okay, so required shape is then cut from the layer. by layer or knife. Okay, so it's cutted by layer and knife, so the next layer is added. So it's going to be really simple. The sheet lamination technique is really wonderful. See, you can just put on the laser thing and just 2 spoons and everything's done, right? So let us go to the next, the seventh one, the final one, right? Directed energy deposition, we also call it as DED, dead. So it consists of a nozzle mounted on a multi-axis arm. Okay, so how each nozzle can move in multiple directions uh, in 360 degrees, and also material is melted upon deposition with a laser or electron beam. So see, it is a laser electron beam. By this, it's a material is melted upon deposition. So how does it works? So also the nozzle mounted multi-axis. So see, A4 or 5-axis arm with nozzle moves around the fixed object. So this is the object that we are taking here. So maybe here like this. So this is the metal wire that we are using, the metal supply wire, and this is a build platform. So what happens here is, the nozzle will be moving across the fixed object, and the material is deposited from the nozzle onto existing surfaces of the object. So across it like this, the material will be supplied. Okay, so it is can be either provided with wire or as the powder form. So the material is melted using the laser, this electron beam, right? This electron beam deposition. So electron beam are plasma deposition upon deposition. And finally, what happens here is the material is added layer by layer, and it solidifies. Okay, solidifies, creating a new model. Okay, so this is the final thing. And so there's few things that we need to remember, that present condition and trends. So there's much technology being developed nowadays, and the model data useful like stereolithic process lithography. It's the first decomposed into this series of 2D, and now it is being finally is it cross-section areas, okay, right? So there's a fed into additive manufacturing machine, so it's used directly and indirectly to produce prototype parts. It's a major technology that's being used here right now, and also manufacturing and production costs also decreasing, and there's be also many used industry collaboration and technology also transfer, which we call TOT, transfer of technology. And there are more and more companies starting beginning of this additive manufacturing technologies, which helps them in reducing the time to market and increasing in product quality and improving of the product performance, and finally the cost is coming into imaginary line. So with this, we're gonna come to the end of the present scenarios. So the metal based additive manufacturing process have recently emerged and super duper applications in one in automobile engines, aircraft assemblies, power tools, and manufacturing tools. Okay, so it includes manufacturing jigs, fixtures, and drill guides. So there's so much of things that we can learn about this public, about additive manufacturing, how it empowers the people to build what they dream and what they desire and what they want to circulate and integrate with. And these materials which are a rapid prototyping of how a part of manufacturing process in their courses. So there are a few other things that I want to add about the future endeavors about this additive manufacturing process. So the first thing about this is technology and research. So the first thing about technology research is the third industrial revolution, we may say it, because it's a cost effective and mass customization of complex products is agreed with this wonderful additive manufacturing process, and also reduce material wastage and energy consumption. Also we can use the best out of waste, and also adapt new product designs, and it is up to your design, up to your capability, and up to your additional expenses. We do not have it just like that. If you're gonna have one material, we can do it by setting up the melting time and everything. So also there is also it's helpful in biomedical field about the fabrication of the tissue scaffolds in our body. It's a biocompatible, biodegradable, and bioabsorbable. We say it as CDA. Okay, CDA. What is CDA? It is compactable, degradable, absorbable. Anything that enters into our body should be CDA, that is compactable, degradable, and absorbable. And educational and training, it holds a potential promoting science, technology, engineering, and mathematics. So we call it as STEM. It's a major branch of education. STEM, science, technology, engineering, and mathematics. So it holds a major cost over there. And also availability of low cost 3D printing equipment is also creating the opportunity for the additive manufacturing, and also hand-on labs in primary, secondary, and post-secondary schools across the nation also helpful in the training process. So there are few gaps and needs that we need to cover to go row in higher heights. What are these things? So the first thing that the gap that should be needed to be covered is the technology and research thing is system integration and cyber implementation. So what are these? So there are four things that we need to remember here. The first thing over here that we need to consider is the materials development and evaluation. So once the material developed and evaluated, we will be having a wider scope of how the material is going to work. Okay, the second thing over here is the design methodology and standards. Okay, design methodology and standards. And third thing is modeling, monitoring, control, and processing. Okay, so the final thing, it is characterization and certification. Okay, so we call this one as to be the four things, which is MDMC. Okay, MDMC is to be given for filling the gaps. So first thing is material development and evaluation, design methodology and standards, modeling, monitoring, control, and processing. Okay, and finally characterization and certification. So this is how it works, guys. So with this we complete and we'll move into the next thing. So yeah, so there's also material. So there's intensive material research and development is needed in metallurgy. Many people who are from metallurgy background, it takes about 10 years to develop a new alloy. You guys know it. And including the determination of various critical properties such as fatigue strength, creep resistance, corrosion resistance, okay, so tensile, and everything else, what it could be. So this time frame also applies to developing new materials for additive manufacturing. So even this existing material advancements also needed in the material parts from the metallurgy people who are seeing this video, and also the design properties and various advanced advancements in addition manufacturing oriented designs to be done. So CAD system should be also reinvented and to overcome its limitations. And also this be we also called as MSCP. MSCP is called modeling, sensing, controlling, and processing innovation. So by this, the difficulties of to predict the microstructures and fatigue properties from additive manufacturing process can be minimized. And also sensing of the additive manufacturing may require fast in situ measurements of the temperature, cooling rate, and also residual stress. Okay, there we go, guys. Finally, characterization certification. So real production environments and practices are much more rigorous than the prototyping process. So we need to have a predominantly rapid prototyping machines for the architectures, and also we need to strong, ductile, flexible materials. Okay, so there's some sort of industry collaboration and technology that I told you before. How does it works is about the visibility towards the time. So technology trigger is over here, and the peak of inflated expectations is here, and we do not much need this so hype of cover. So we can see it, right? So the basic thing about here that we can little bit go into further is about how the technology trigger had been changing, how the kicks off and how the products exist, and also peak of inflated expectations, how the publicity produces, and also disillusionment, how interest wanes, and also slower alignment, plateau in production, how we've seen this before. So this is all about the full advantages of the admin will require educating the current workforce, recruiting a new generation of students, developing proper designs. And few of the recommendations that from our side is in the materials and metallurgical point of view, new materials are to be needed for the additive manufacturing process. That is very easy to control even by the layman. Okay, so the formation and mixing of materials is desired forms with desired properties also needed for the maybe biomaterials, maybe defense and point of view. And design point of view, my suggestion is about methods and tools for simultaneous multifunction is also required, and product design and additional manufacturing process design is also required, and modeling, as we told before, STEM, science, technology, engineering, and mathematics. So modeling is also required in the robust physical based mathematical models of temperature and stress, so that we can get the prediction of microstructure fatigue properties resulting in the extreme heating and cooling rates. And finally, sensing and controlling. So fast response sensors for detecting defects and phase transformations, integrated real-time sensing and closed loop, and also finally additive manufacturing become hugely successful. So these are the few collaborations, teaching factors and things. So finally guys, thank you for being with me till now, and right now we're going to see a very important thing, that the conclusion, right? So the process of joining materials to is called layer by layer in 3D format is called additive manufacturing, right? So the second thing that we need to remember here is traditional subtractive method techniques rely on removal, but whereas our technique doesn't need cutting or milling. Our technique only needs addition, adding. So has many advantages over the traditional manufacturing process, has 7 processes of additive manufacturing. Additive manufacturing is a shifting of pure rapid prototyping technology. We have all seen this. And guys, there is a manufacturing metal components with virtually no geometric limitations of tools offers to increase product performance and new process and revenue streams. Okay, so this is all about guys. We have learned so much about this additive manufacturing. Do you have any doubts? Just put in the comment section, and these are the references that I got from, and you guys can also just go into, just take a screenshot of it. And thank you. And if you want the PPT, just put your mails and we can send it to you. Thank you. Good day.